Yeah, so since embedding layers can be a pretty complicated concept at first, let's actually now take a look at a few PyTorch code snippets to further illustrate how these embedding layers work. So the context here again is that we have a recurrent neural network that predicts one character at a time. And for each input character, we represent this character as a one-hot encoded vector. And for example, if we have the word sunny with 5 input characters, we go from the one-hot encoded representation here at the top to this dense representation with 5 rows using the embedding layer on the right. So in the previous video, we learned that embedding layers are efficient forms of matrix multiplications when working with one-hot encoded vectors. Now let's take a look at a concrete example using the torch and n embedding layer implemented in PyTorch. So when working with embedding layers, we represent our inputs as indices. So suppose we have 3 training examples here with the indices 2, 3, and 1. And note in practice, each index here would correspond to a character. For that, we could use a PyTorch dictionary to map from characters to integers. But yeah, for simplicity, we skip the mapping from characters to integers here. If you are curious about that, don't hesitate to reach out via the forums and I'm happy to explain further. Now let's focus on creating the embedded vectors. So for that, suppose we want to create embedding vectors with 5 dimensions. And we also create a variable here for the number of indices. The number of indices is computed by taking the max index, so the highest index, and add a +1 to it. So in this case, since we usually start with indexing at 0, in this case, since we have a 3 here, this would be 3 + 1 = 4. Now, using these 2 input parameters, we can initialize our embedding layer as shown here. Yeah, and since we have 3 training examples here, our output matrix will consist of 3 rows. And since we specified the embedding dimension to be 5, we will have 5 columns here. Yeah, since this was a bit fast, let's summarize this process step by step. So we start with the 3 training examples, which we represent as indices here. Then we construct the 4 × 5 embedding matrix here, where the number of rows corresponds to the number of indices. And the embedding matrix here has 5 columns, since we specified that we want embedded vectors with 5 dimensions. And then we use this weight matrix, the embedding matrix, to do a simple lookup based on the index positions to obtain the encoded vectors. So this is in a nutshell how the embedding layer works. Let's now see if we can reproduce the same results using a linear, a fully connected layer in PyTorch. Yeah, and since our linear layer does not do an index-based lookup, we now have to encode the inputs specifically and explicitly in one-hot encoded vector form. Yeah, then we are also initializing here our linear layer, where we also specify that we want to have 5 output dimensions. Note that due to the nature of how the internal matrix multiplication works in nn.linear, we are also using a transpose here so that we can get the equivalent results compared to using the embedding layer. Yeah, and this is all there is to it. So if we now carry out the matrix multiplication here, you can see that the results are exactly the same compared to using our embedding layer. So in other words, the embedding layer is just a more efficient form of matrix multiplication if we have sparse inputs, for example, one-hot encoded inputs. And again, because this was a bit fast, let's summarize the linear approach here step by step. So we start again with the indices, but this time we encode them into this one-hot encoded representation explicitly. And second, we initialize the weight matrix. And then once we have the encoded inputs and the weight matrix, we multiply those two to get the encoded outputs. Yeah, and in a nutshell, this is how embedding layers work and how they compare to the fully connected layers. In the next video, we will now introduce the attention mechanism and the transformer architecture.